Hi everyone! In this video we're going to learn the approach for graphing the secant and cosecant functions. We're going to use the basic cosecant function as an example. To understand the nature of the graph of this function, we need to recall that cosecant function is the reciprocal of sine. So the sine function will be the key to understanding how the graph of the cosecant function will be positioned. And for this reason, I'm going to start by sketching the graph of the basic sine function. Here it is. Now let's go back to this fraction, 1 over sine of x. That's what cosecant equals to. Remember that denominator of a fraction can never be equal to 0, because otherwise you will be dividing by 0 and it's undefined operation. So, this reminds me that in some cases, cosecant function can be undefined. And that's when the denominator, or in other words, sine of x, equals 0. In other words, cosecant function is going to be undefined for all values of x that have sine value 0. So where do we find those x values when we look at the graph? Well, it's actually easy because remember we have points on the graph that we call zeros. And the reason they call zeros is because at those values, function value is 0. In this case, sine value is 0. So it's easy to locate those values when we look at the graph. So when x equals 0, pi, 2 pi, 3 pi, sine is 0. And because of that, at those values, the cosecant function is undefined. This function does not exist at those values. Now, how will that look like on the graph of the cosecant function? Well, whatever shape it has, the graph cannot have any points at 0, pi, 2 pi, and 3 pi. Instead, at those x values, there will be asymptotes. So asymptotes are the lines that the graph will approach but never touch. These are kind of like borders that graph cannot cross. And if we think about it a little bit more, then we're going to realize that, well, that means that graph of the cosecant function is not going to be continuous as the graph, let's say, of the sine function. It's a continuous wave. It never stops. It never interrupts. And since these asymptotes are like the walls that graph of the cosecant function cannot cross, we make a conclusion that it will consist of pieces. They're actually called branches. Let's try to figure out where they're going to be positioned. Let's look at the unit circle to get some hints. We know that at pi over 2, sine value is 1. Well, reciprocal of 1 is 1. So that means that at pi over 2, sine and cosecant have exactly the same value. So that means that graphs of the sine and cosecant functions are going to meet at this point. Same happens at 3 pi over 2. Sine of that value is -1. Well, reciprocal of -1 is -1. And that means that the graphs of sine and cosecant function are going to meet at this point as well. And that's going to be the pattern. Graphs of the sine and cosecant functions are going to meet at the minimum and maximum points of the sine graph. So here's another one. Now let's try to analyze and understand where the rest of the points of the cosecant graph will be positioned. I'm going to look at the unit circle again. And specifically, I'm going to focus on the second quadrant as the angle increases from pi over 2 to pi. This means that I am focusing on this interval of the graph. As the angle increases from pi over 2 to pi, what can we say about the sine value? Well, remember, sine corresponds to the y-coordinate. So what can we say happens to the y-coordinates as we move along the unit circle this way? Notice how we're getting lower and lower along the y-axis. So it means that the y-coordinates are getting smaller and smaller until they approach 0. And the sine values are in the denominator of this fraction that equals to cosecant. Now, what happens to the fraction itself when denominator gets smaller and smaller and smaller? Well, the overall value of the fraction becomes bigger and bigger and bigger. And because of this behavior, the graph of the cosecant function on the interval from pi over 2 to pi is going to have this shape. So it's going to be getting larger and larger and larger. So it's going to be approaching the asymptote. However, it will never cross or touch it. And now let's see what happens on the interval from 0 to pi over 2. So as I rotate, the angle from 0 to pi over 2, I can see that the sine values, which correspond to the y-coordinates, are getting larger and larger. And eventually, as I'm getting closer and closer to pi over 2, the corresponding y values are getting closer and closer and closer to 1. So that means that starting with extremely small values of sine, and it's in the denominator, so it means that the cosecant function values are extremely large. As the sine value increases and approaches 1, it means that the denominator is increasing and approaching 1. The overall fraction are going to be getting smaller and smaller, and it will be approaching 1 as well. So as we move from 0 to pi over 2, part of the graph representing cosecant function will be decreasing and approaching 1. However, it's common to put arrow on this end just to indicate that this curve does not have a starting point. And if we continue in this manner and analyze the behavior of the cosecant graph on the interval, let's say from pi to 2 pi, in between these two asymptotes, it's going to be exactly the same approach. The only difference is that since we are working in this bottom portion of the unit circle between pi and 2 pi, the y values here are negative, and as a result, cosecant values are also negative. So the branch of the cosecant graph will be down here. It will be facing down. And here's one more branch because pattern is going to repeat. And as already mentioned, these portions of the cosecant graph are called branches. So here's one branch, here's another branch, and so on and so forth. So let's summarize what we've learned so far. First, we learned that sine function really helps us to understand the behavior of the cosecant function. And in fact, this is how we graph the cosecant function in general. So the graph of the sine function is called the guideline graph because we always start by sketching it. And then it helps us to find asymptotes of the graph of the cosecant function. So asymptotes are placed at zeros of the sine function. We learned that the graphs of the cosecant and sine functions meet at maximum and minimum points of the sine function. So that's where the branches of the cosecant function will be positioned. And the branches themselves have this U-shaped form. They're always in between two neighboring asymptotes. They open wide enough to approach asymptotes, but they never touch or cross them. And the branches positioned at the maximum points are always open upwards, and the branches positioned at the minimum points are open downwards. And this pattern repeats forever to the right and to the left along the x-axis. I removed all supporting information from the pictures so that we can only see the graph of the cosecant function. So the graph itself is what we have here in blue. Now let's look at this graph again and add a few more properties of this graph. So first of all, this pattern continues forever to the right and to the left. Now you can also see that there are no x-intercepts for the graph of the basic cosecant function. Of course, if we shift it up or down far enough, well, then we're going to start seeing some x-intercepts, but the basic cosecant graph does not have any intercepts. Also notice that there are actually no maximum and minimum points. Well, I can't really call this a minimum point because I have values of the cosecant function that are lower than that. And I cannot call this maximum point because I have points on the graph that are higher than that. And because there are no minimum or maximum values, the graph of the cosecant function does not have amplitude. And finally, let's talk about the period of this cosecant function. Remember that period is the length of one cycle. That means that to figure out the period, we have to first look or find one cycle of the graph. What is the cycle? Cycle is one copy of the repeated pattern. In other words, portion of the graph such that if you copy and paste it, you can recreate the entire graph. Let's think what that should be in this case. Well, if I take this one branch and then copy and paste it, will I obtain the entire graph? No, because if I copy and paste this branch, I will only have upward-looking branches, and that's not how the graph of the cosecant function looks like. That means that I actually need two branches, the one that looks upwards and the one that looks downwards, to have a cycle. So if I take those two branches and then copy and paste them, then I will recreate the entire graph. So that means that the distance along the x-axis that covers those two branches represents one period. And in this case, from 0 to 2 pi, well, it's 2 pi. And if I bring back the graph of the guideline function, the sine function, then I can see that it's exactly the same as the period of that function. And we can generalize that. The period of the cosecant function will always be the same as the period of the corresponding sine function. So this is what we learned about the graph of the basic cosecant function. But can the cosecant function have some numbers within it? Can we put any numbers in front of cosecant? Or can we put a number in front of x? Can we translate the graph? Can we shift it to the right or to the left, up or down? Yes, we can. In other words, the cosecant function can have this form. Now it looks way more complicated. How do we graph it in this case? Well, there's a good news. Pretty much everything we talked about is going to stay the same. First, we need to remind ourselves that cosecant is the reciprocal of sine. And this will allow us to obtain the guideline graph that is dressed up same way as the given cosecant function. Notice that the sine function has same values a, b, and c within it. Do we know how to graph it? Well, yes, we learned that. So we start by graphing this function, and then the graph of the given cosecant function comes along with it. Okay, so we talked about the graph of the cosecant function quite a lot. And now we have pretty good understanding on how to produce that graph. How about secant function? Well, the steps are going to be pretty much exactly the same. We start by reminding ourselves that secant function is the reciprocal of cosine. So in this case, cosine function is going to be the guideline graph. Once we graph it, then we're going to repeat the steps. At every 0, we're going to place asymptote. Branches of the secant function are going to meet minimum and maximum values of this cosine function, and they're going to be U-shaped branches looking from far away exactly the same as the branches of cosecant function. Okay, so of course it's important to do an example where all that takes place, and you're going to see it in the next video.